Hi, this is Dan with Apex Tutoring, and we're answering this question for Sam. He asked us this question about the statistics of quality and reliability about a machine part. And this part has a mean of 75.51 millimeters with an LSL of 75.29 and a USL of 75.71 and a standard deviation of 0.08 millimeters. Any part above the USL is reground for a cost of $3.10, and every rejected part below the LSL costs $4.65 for parts and labor. A modification to the machine costs $6,200. This brings the standard deviation to 0.04 millimeters. How many parts of production, including good and bad parts, does it take for this modification to pay for itself? So the first thing that we need to do is take this information about the mean, the LSL, the USL, and the standard deviation, and we're going to calculate some z-scores. So the z-scores, assuming that this is a normal distribution, is basically going to tell us how much area we have within a certain number of standard deviations from the mean. So what we mean by that is if this is our standard distribution, and we have our mean right here, and we find out this area here, that's going to tell us basically our chance of having a part if this is our standard deviation, how much chance we have of that part failing. Okay, and we'll look for that both above and below. Okay, so the first thing we'll do is we'll find the z right for the right hand side, and that is going to be the USL minus the mean divided by the standard deviation. So if we do that, we look back at our numbers, we had 75.71 and 75.51 for a value of 0.20 and a standard deviation of 0.08, which is going to give us a z value of 2.5. We do the same thing for z left, which is going to be LSL minus the mean over the standard deviation, and this will give us negative 0.22 if we do this subtraction correctly over 0.08, which will give us negative 2.75. Now, what we want to do is take this z-score and convert it into a percentage of the area, okay, for this normal distribution. Once we have the percentage, we can find our expected cost as previously by taking our percentage and multiplying it by the cost of the outcome. And in this case, for the upper limit, we're going to have to pay an extra $3.10, and anytime we're below the lower limit, we're going to have to pay $4.65. So this is going to be $3.10, and this will be $4.65. Now this percentage that we're going to calculate, or rather look up in a table, is just going to tell us the chance per part. So when we do this expected cost, this is going to be per piece, which is very important later on. Okay, so when we do this, we're going to get a percentage of 0.621% when z is 2.5, and when z is negative 2.75, we're going to get a percentage of 0.298. Okay, so our expected cost for z right is going to be 0.621% times $3.10, which is going to be a very low number. It's going to be $0.01925 per part. Similarly, so this is the expected cost on the right side. The expected cost for the left is going to be the same thing, 0.298% times $4.65, which is going to give us 0.01386 per part. Now, here's where things get interesting. The new part has a standard deviation of 0.04. And if you calculate the new z values, you get 5 and negative 5.5. And the percentages that correspond to this is 3 times 10 to the negative 5th percent and 2.1 times 10 to the negative 6th percent. So, in other words, we can pretty much assume that these chances are now close to 0. Close enough to 0 that it's not really going to affect our next step. And our next step is simply to find out how many parts it's going to take to make up the $6,200 that we are investing in our new machine. And this is something that business owners have to calculate all the time to see whether or not a machine would be worth it and how long it would take to break even. So our machine actually costs us $6,200, and to find the number of parts, we're simply going to divide this by the amount that we are paying per part. And we have a chance of paying 0.01925 per part if we are above the limit, and we also have a chance of 0.01386 per part, running out of space a little bit, if we're below the limit. Now, if you do that calculation, you will find that it is required to make 187,255 parts, depending on your rounding, in order to break even. Now, this is going to include the good parts and the bad parts. So we'll call that N, the number of parts. And that is our final answer. So thanks again for asking us this question. And we're always here if you have any other questions about math, physics, biology, chemistry, or any other science class. Thanks very much and have a great day.